Yeah, hello. So hi, nice to be there virtually. Sorry, I can't be there in person. I guess I'm not sure how many of you there are there, but I can see a few in the Zoom window. Um, so this is going to be a, somewhat well, I don't want to say crazy talk, but it's going to be about trying to resolve some difficult conceptual puzzle in quantum gravity. And I don't claim to know all the answers for everything. So I'll try to tell you the story as I currently understand it. But I'm happy to have questions and discussion throughout the talk. So please don't be shy if you want more details on something or you have some comment that you want to make. Um, so I guess I'm not sure if I'll be able to see the hands. So I'm not sure how you guys handle questions. You can just shout them out, I guess, or I'll try to ask for them occasionally.
You speak out when you have questions.
Yeah, okay. Um, so so this talk is based on recent work with Misha Usat-Yuk, who's a postdoc at KITP, and with Ying Zhao, who is a postdoc here at MIT with me. And so what I'm going to talk about is this somewhat crazy idea that if you do quantum gravity in a closed universe, meaning a closed spatial manifold, like say S3 or T3 or something like that, um, then the dimension of the Hilbert space of a closed universe is 1. So in other words, in a closed universe, there are 0 degrees of freedom. So when I first heard this idea, I thought it was surely not correct. Something that there must be some mistake in the argument, something like that. But over the last few years, I've tried to understand it better. And currently, my understanding is that if you want to believe um, the kinds of arguments which we've used to learn more about the black hole information problem in the last 5 or 10 years, inspired by ADS CFT and so on, then the same kind of ideas seem to lead you to this conclusion. And so we need to figure out what to say about it. So I'll try to give you some of the arguments that this is true as we go on so that you can see. And so since but if we accept that this is true, then we have an immediate problem because, well, how can you fit the richness of human experience into 0 degrees of freedom? And if you can't, does that mean that we've somehow experimentally ruled out the possibility that we could be living in a closed universe, without even say needing to build a telescope or something like that? We just kind of, by virtue of the fact that our lives seem interesting, we know we don't live in a closed universe. That seems like a sort of radical claim to make. Sorry for my cough. And so in this talk, I'll try to convince you that there is at least some sense in which one can try to make sense of this statement, but fit it into a theory which is rich enough to make room for semi-classical physics in a closed universe as we would sort of naively expect it to work. Okay, so let me try to say a bit now about how we get towards this. So one way to package what we've learned from thinking about ADS and thinking about black holes is that the way you should think about the emergence of space-time mathematically, or really the emergence of anything, is that there should be some linear map which takes some Hilbert space of the effective degrees of freedom, the emergent degrees of freedom, and maps that Hilbert space into a Hilbert space of fundamental degrees of freedom. So there are many examples of this in physics, right? So for example, the the effective Hilbert space could be the Fock space of phonons, like say in that table that I see in your lecture hall. Whereas the fundamental Hilbert space is the Hilbert space of the standard model, right? So it has some subspace living in there that describes the excitations of the table. Looks like the quantum field theory of the phonon excitations, but it's really, embedded into this larger Hilbert space of the standard model. Other examples are easy to come up with. For example, the effective description could be hadrons, and the fundamental description could be QCD. An example which has inspired a lot of the recent progress is ADS-CFT, where you take this effective Hilbert space to be the Hilbert space of ADS excitations near vacuum, and then this fundamental Hilbert space is the Hilbert space of the boundary CFT. And then most recently, we've had an example of this where we have on one side the black hole interior, say the modes of low energy fields inside the black hole on some nice Cauchy slice. And then this gets mapped to the Hilbert space of black hole microstates, which has, say, dimension e to the a over 4g. So all of those things are examples of this idea where you have a linear map going from some effective description to some fundamental description. This last example is a bit unusual. In the other examples, the fundamental Hilbert space is bigger than the effective Hilbert space. So for example, QCD has lots of states that aren't so useful to think about in terms of hadrons, but then, the nice low energy ones are hadrons. And similarly with the table, right, there are lots of states of the standard model where the table isn't there at all. So they're not in the image of this map V. But in the black hole case, the thing that's so confusing is that if the black hole evolves for a long time, then the interior gets bigger and bigger. And eventually there's too many modes in the black hole interior, too many low energy modes to all fit into the Hilbert space of black hole microstates. And that's the origin of the black hole information problem. And so this particular example, we've learned in recent years to describe by saying that the map V is non-isometric, meaning that it doesn't preserve the inner product, and indeed it can't because it's going from a bigger Hilbert space to a smaller Hilbert space, whereas the other examples would have been at least approximately isometric in the sense of preserving the inner product from the effective description into the fundamental description. So evidence for this picture of emergence has come from various directions. Of course, for QCD and tables, it's an old story. But for quantum gravity, right, so from ADS-CFT, this seems to be how it works. So this map V is called the encoding map that maps the emergent space-time degrees of freedom into the fundamental. And so we've understood a lot about this map in ADS-CFT. But then outside of ADS-CFT, we also have these two powerful tools. There's the so-called quantum extremal surface formula, which is a tool for computing entropies in gravitational systems. And more generally, there's the gravitational path integral in the form of Gibbons and Hawking, where you say you fix some boundary features of the space-time, and then you sum over everything that you can fit inside of those boundaries. So, for example, for the evaporating black hole, there's this picture you may have seen. So here's a flat space black hole. Here's its event horizon. And you imagine there's some Cauchy slice here, where I've sort of arbitrarily split the system here into the degrees of freedom that are far from the black hole, and then the things that are near or inside the black hole. And so maybe inside the black hole, there's some right-moving degrees of freedom, there's some left-moving degrees of freedom, and then out here in the radiation, there's some outgoing degrees of freedom. And then what we learned in recent years is that if you try to compute the entropy of the radiation, if you just naively do it using the semiclassical picture, you'll get information loss. You'll find that the entropy of the radiation goes up and up. But if you instead use the QES formula of the path integral, you'll conclude that the so-called entanglement wedge of the Hawking radiation includes not just the Hawking radiation, but also this so-called island in the black hole interior. And if you include that, when you use the QES formula, then you get a page curve that goes up and then goes down. And you can try to motivate that by using the gravitational path integral. Okay. So that's sort of my review of what we learned so far. I'll pause and ask if there are any questions so far. Okay. So you could ask in this black hole example, what is this map V? And so let me try to say that a little bit more explicitly. So what seems to be a good model for this map V is that you have some big unitary transformation, and you feed in the left and right moving black modes in the black hole interior. You get out some state in the Hilbert space of black hole microstates, but then there's some kind of projection here, and then it turns out to be a good idea to normalize by the square of the dimension of the Hilbert space that you projected onto a fixed state. So this map doesn't obviously preserve the inner product because it's going from the interior degrees of freedom to the black hole microstates. But because of this projection that I put here, it's not a unitary, and in particular, there's no reason for it to preserve the inner product, at least not exactly. But there's a sense in which it approximately preserves the inner product, and that's the story of the non-isometric code giving an explanation of the emergence of the black hole interior. You somehow have this map that goes from the low energy effective modes into the microstate degrees of freedom. And so somehow by using a model like this, you can reproduce a lot of the things that you can derive from the gravitational path integral. Okay. Okay, so now let's go to the closed universe. And so I'll first kind of tell you some answers, and then I'll try to justify those answers in the remainder of the talk.
Can I ask a quick question?
Yeah, please go ahead.
So this state B that you get out is a member of HB, right? That's the
yeah, that's right. That's right. Yeah.
And what's the bra zero with the
Yeah, that's just some fixed state. So the idea is U maps you into a larger Hilbert space than just B, but then you include a projection onto some particular state 0 in those extra degrees of freedom, which I call P for projection.
Okay.
Yeah. Somehow my scroll is not working here. Let me just see if I can do this. Okay, I mean, I can do it like that if I have to. Okay. Maybe I have to do this. Hold on. I'm out of practice doing this, but it worked when I did it before. Okay, well, I think for now it's okay. I'll just do if I have to, I'll do the thing where I zoom out and zoom in to scroll side to side. Okay, so except I want full screen. Okay. So good. So now let's go to the closed universe. All right, and so first I'll just say a proposal. So when we say that the closed universe is one-dimensional, that the fundamental Hilbert space is one-dimensional, what I really mean is that for this map V, there's some picture not too different from this one, except now I put some orthogonal matrix instead of unitary for a reason I'll explain in a moment. I feed in S, which just means, whatever degrees of freedom are in the closed universe. It turns out it's a good idea to have some fixed state psi naught that I feed in as well. That's just if I want to restrict the input I can put here. You can ignore psi naught for now if you want. But now the key thing is that I just do a complete projection on everything that comes out of the map. So there's no microstate Hilbert space left over, right? I'm going from some, so here's my closed universe. The Hilbert space of semiclassical states, I'll call HS, so S is the system, the closed universe system. And then to map it to the fundamental holographic description, I just project it. I hit it with some complicated orthogonal matrix, and then I do a projection onto some fixed state 0. Now, let me just comment for a sec on why I made it orthogonal. This is because in a closed universe, CPT is a gauge symmetry, because in quantum gravity, there are no global symmetries, and CPT is always a symmetry, so it has to be gauged. And so if you gauge an anti-unitary symmetry, it makes the Hilbert space real, and so this map has to be orthogonal instead of just unitary. So had I given this talk a year ago, I was given a whole talk about that. But for now, let's just say it's true. So it has to be orthogonal instead of unitary. And so, this kind of thing that I drew here, right, this is a rank 1 projection, or it's proportional to a rank 1 projection, right? It just, you feed in whatever state you want here, and it just projects you onto this state, 0 times O transpose. So this is a pretty crazy proposal for a fundamental theory of nature. It just takes whatever low energy state we have, and it projects it onto this one state. So let me try to give you some sense in which it's crazy. So let me tell you. So I haven't told you what O is, but to try to get a sense of what sort of will happen for a generic choice of O, we can get at that by averaging. So let's say we compute on average in the Haar measure on the orthogonal group. What we get if we kind of encode two different states, psi and phi, and then take their inner product. Okay. And so since people are pretty good at integrating over the orthogonal group, you can do this integral. And actually, what you get is just the inner product of phi and psi. So that's maybe a little surprising. It says on average, this rank 1 projection preserves the inner product. But of course, preserving it on average is very different from saying that some particular O is likely to preserve the inner product. And indeed, if we look at the fluctuation of this statement, so we look at, phi v dagger v psi minus phi psi squared. Okay, so this is the typical fluctuation. You get 1 plus the norm of phi psi plus order 1 over d. Okay. So in other words, you see that there are large fluctuations in the comparison between the sort of encoded inner product and the unencoded inner product. And that's really not surprising, right? Because this, this thing where you take whatever state and you just project it onto one state, and then, how can that possibly preserve the richness of the larger Hilbert space? It can't. And so even though maybe on average it does, for a fixed O that you just pick, the inner product will not be close to being preserved. It will have error, which is order 1, which is kind of, so the sort of signal to noise ratio is 1. So this is if you like, this V here is a bad encoding map. By the way, I'll ask, can you see my cursor when I move it around?
Yes.
Okay, good. Just making sure. Yeah, and so somehow we need to, if we want our encoding map to be a rank 1 projection, then currently it seems like we're in the situation where we can just rule out the theory by, waking up in the morning and looking at the alarm clock and seeing that it looks approximately, like quantum mechanics, instead of having these huge fluctuations in just sort of anything that you would observe. And so my goal today is somehow to propose some kind of fix for this. Okay, I still haven't tried to convince you that this is true. I'm going to do that in a moment. But if it's true, then there's clearly some big problem that needs to be solved. Okay, so far so good.
I have another clarifying question. So when you say universe, do you mean, I think you already mentioned that this is some sort of a closed manifold, like a compact
Yes.
or S3 or something like that?
Yeah.
How about the expansion of the universe?
Uh,
To play.
yeah, as long as the Cauchy slices are compact, expansion doesn't help you. Yeah, which I agree it's a bit counterintuitive because you'd think if we're in an expanding universe and we've undergone a million e-folds of inflation, how can we possibly tell whether the topology is closed or not, right? It's a very reasonable complaint, and that is the complaint I made in the beginning. How can we possibly tell just by doing local experiments? But somehow, if the Hilbert space is really one-dimensional, then it seems like we can tell because physics just doesn't make sense if it's closed. And so then since physics seems to make sense, it isn't, right? But I am offended by that, just as I think you are, because it seems like we shouldn't be able to tell. Okay. Any other questions? All right, so I have to do this annoying Zoom thing. Sorry. Okay, so now let me just say what my proposed resolution is. What just happened? Okay. Now it's okay. That's better. Okay. So the proposed resolution is proposal is that we need to include explicitly the observer who does measurements. Okay. So I have to acknowledge that this, I mean, this sounds a bit like the emails that I get, every day from weird people, telling me that the universe doesn't have any degrees of freedom, and to understand quantum mechanics, you need the consciousness of the observer and all this. And so it's a bit embarrassing for me to be saying this in front of you in a seminar. But I'll try to convince you that there's some calculations behind this. When I say this include explicitly, I mean something fairly concrete, where you can compute stuff and see to what extent it does or doesn't fix this problem. But I'll still acknowledge that it's still a bit crazy. And the justification for that is just that the problem is really serious. And so any resolution that works is going to have to be crazy. Okay, and so what do I mean more explicitly? So I'll first just draw a picture, which maybe it won't make too much sense, and then a bit later I'll try to motivate the picture some more. So I'm going to introduce a alternative holographic map called VHAT. And so what it's going to do is there'll still be this normalization factor. I'll still have this orthogonal matrix over here. There'll still be this projection onto a definite state, this rank 1 projection. But now I'm going to say a bit more about, there'll still be this fixed state here, although it's not too important, so you can ignore it if you want to. But what I'm going to do now is I'm going to split the input in the bulk into two parts. There will be a part which I'll call capital M, which stands for matter. So this is going to be the degrees of freedom in the universe that the observer wants to do an experiment on, wants to learn something about. And then the other line here will be the observer themselves. And what I will do is I will demand that the observer is entangled with some external system I call OB prime in some fixed state, which I'll call omega, which is an entangled state between OB and OB prime. Okay. Now, let me, before trying to motivate this, I'll motivate a little bit in a moment and then more later in the talk, but let me first just say mathematically why this might be a good idea. So here you see the information of the matter system is, being fed into this rank 1 projection just as before. So the rank 1 projection is still there. But now I've somehow got this extra external system floating around, which has a Hilbert space that can have a larger dimension. And if you've learned about quantum teleportation before, you can see that there's actually a way for information about the matter system here to end up in this OB prime here, because it can kind of go up here. The post-selection can kind of quantum teleport it down through this entanglement, and it can make it out up here. And in fact, that's the same kind of mechanism that showed up in the page curve calculations, where because of the non-isometric code, there was some teleportation where information got teleported out into the Hawking radiation. Here, it's a little bit less clear what's the physics of this OB prime, because the whole universe is just these lines here. And so this OB prime is something that's outside of the universe and somehow entangled with something inside the universe. And it's kind of on me to convince you that this is a reasonable picture to draw if I want to know what's happening inside of the closed universe. So let me just make two sort of anticipatory comments about why I have this entanglement and why I have this external system here. So the entanglement here that I say is sort of fixed, I want to say is caused by decoherence with the environment E, so that in the universe here, there'll be some environment which is interacting with the observer, and because they're interacting, the observer will get entangled with the environment. So that's the source of this entanglement, the idea that it's sort of, this entanglement can't be avoided. And then the cloning step, where I put a copy of the observer out here, this OB prime, who's entangled with OB, I'm going to say as a consequence of making the observer classical. And here, the idea will be that you can't really talk about an observer in any sensible way unless you make them classical. That's the old, Bohr argument about the Heisenberg cut. And we'll see that somehow when you try to make the observer classical and think about it a little bit, you can sort of interpret it as defining a map V hat like this. And then the main message of the talk is going to be that once you define V hat like this, then now this is something that does reliably preserve the semi-classical description of space-time. It's sort of consistent with what we know. And so I'm going to claim that this preserves effective field theory, the semi-classical description, up to errors which are of order e to the minus the entropy of the observer. Okay. And so let me put a box in this. This is sort of the slogan of the talk. So since I don't necessarily expect you to follow all the details of the calculations, whatever, the idea is that if you're willing to accept a theory that is only accurate up to the entropy of the observer, the number of degrees of freedom in the observer, then I can give you one by using this decoherence and making the observer classical. Okay. And so, this, maybe sounds crazy to you. Feel free to complain. I'll now stop and ask for questions. Hopefully it will sound less crazy as I go on through the rest of the talk. So this is the end of my introduction, and hopefully you get some at least sense what I'm going to claim. So yeah, now I'm happy to have more questions.
This environment E,
Yeah.
trying to think of this as being something separate from the closed universe, but sort of tensored in and then.
No, it's part of the closed universe. So yeah, if I draw this picture more carefully, I should sort of split. I should put a split here, and then this is E and this is OB. So the environment is part of the closed universe. It had better be, because the observer is in the closed universe, right? The observer is part of the system. That's kind of the basic problem here, is doing quantum mechanics where the observer is part of the system.
So what's different here than just simply, like partial tracing the observer's degrees of freedom out?
Yeah, so we're going to see that basically what I'm going to do is I'm going to take the effective field theory description, and then I'm going to just brutally throw away the off-diagonal components of the density matrix for the observer. With the excuse being that if anyone could measure those, then you wouldn't be an observer anymore. Because those off-diagonal, those are to measure those, that's where somebody sort of recoheres you. And it's some operation that involves erasing your memories and taking things that you thought happened and making them unhappen. And so I have to insert into the usual rules of quantum mechanics some mathematical device that makes sure that that can't happen. And that's basically what this cloning is. This cloning ensures that the entanglement between the observer and its environment can't be recohered. And so the claim is you can't have a sensible theory of the observer at all until you've imposed a rule that the observer can't be recohered.
Can I sort of think of this proposal as being sort of like fine-tuning the definition of what an observer is?
Yeah, well, I wouldn't say it's fine tuning, but yes, it's using features of it's sort of forcing the observer to be classical. Yeah, and so in some sense, I would say it is a modification of quantum mechanics, which again is, as I said, it's a crazier talk than I usually give. But I don't see how to make sense out of a one-dimensional Hilbert space without some kind of modification of quantum mechanics. But I think it's fairly well motivated, because in the end, observers should be classical. To the extent that it isn't, it's not an observer.
If I may ask a question,
Yeah.
historically, what kind of attempts have been made with regard to inclusion of observer in quantum mechanics, and how does your approach compare to those previous approaches?
Yeah, so this formalism of decoherence and cloning and so on, it fits nicely into the work of Zurek and others on decoherence and what they call Ein selection. So we found that, for example, Zurek has a nice review, not PRL, RM, Reviews of Modern Physics about this stuff. So I think we're certainly using the ideas from the sort of more reasonable people who think about that kind of thing. I mean, most of us, we try not to think about these things, but there are people who think about these things, and I think the sort of the work of Zurek and his collaborators on decoherence is pretty respectable, I think, and we're certainly using the ideas from their work. But we're going a bit further, because for them, this decoherence is always just some, for all practical purposes kind of thing where, oh, if somebody came from the outside of the system and really had complete control, they could recohere the observer. And I'm somehow going to modify the rules a bit so that they can't. And, roughly speaking, so we had a joke about this in the paper. To me, the Hilbert space of the whole system in quantum mechanics, that's the Hilbert space for describing experiments that are done by somebody who's external to the system. And in a closed universe, there's nobody external to the system. And so then that's maybe one way of interpreting the one-dimensional Hilbert space, is there's no external observer who has a right to a non-trivial Hilbert space for the whole universe. So we had some joke about the theological implications of that, which I'll leave to your imagination.
Okay, thank you.
Mm-hmm. Okay, so that's the end of my introduction. Let me now try to now get into the more technical part of the talk, such as it is. So I'll now try to review a bit why it might not be a crazy thing to think that the Hilbert space is one-dimensional. Okay, so arguments. Okay. So the first one is based on this entanglement on the quantum extremal surface formula. Okay, so none of these arguments are original to this paper. I'm just telling you to them because if you're not convinced of this crazy thing, then you're certainly not going to buy what I tell you. So let's imagine we have a closed universe, and let's say it has some degree of freedom here, okay, which I call capital S. Some degree of freedom tells you what's going on in the closed universe. And let's imagine I have some auxiliary system over here, S prime, outside of the universe, somewhere else. And I want to prepare an entangled state between whatever's going on in the closed universe and some other system. And let's call that entangled state chi. Now, what I want to do is, so in effective field theory, this is what I have. I have some, qubit or something, qdit something in the Hilbert's in the closed universe that's entangled with something else. So then what the quantum extremal surface formula says is to compute the entropy of S prime, the system that's entangled with the closed universe, I should take the minimum over possible entanglement wedges. So certainly one option is I say that the entanglement wedge is just the system S prime. And if that's true, then I just should get the entropy of the state chi on S prime. So that's like the Hawking answer for the black hole, that the radiation just gets more and more entropic. But then there's a competing option, which is where I include this island here, which is just the whole closed universe, as part of the entanglement wedge of S prime. And if I do that, well, then since both of these are in the entanglement wedge, then there's no contribution from the entropy of chi. And there's also no quantum extremal surface because this surface, the blue dot in the blue circle here, has no boundary. So the alternative is 0. And of course, the minimum between this and 0 is just 0. And so what you learn is that try as you might, you can't entangle a degree in a closed universe with anything else. If you try, it just won't happen. And that's because really there's only one state in the closed universe. Okay. So that's one argument based on the quantum extremal surface formula. Any question about that argument? Okay, so let me tell you the next argument. So this is based on the Graham matrix. So this will be a path integral argument based on the Graham matrix. So say I have a set I of closed universe states. Okay, so I can define an inner product matrix MJI to just be the inner product between J and I. And then the claim is that the path integral tells us that the trace of m to the n is equal to the trace of m to the n with the parentheses outside. And from linear algebra, this is if and only if the rank of m is 1, okay? And so this is some argument that however many states you think you can prepare, if you take their span, you'll find that it's one-dimensional. Okay, so let me now try to tell you why the path integral says this. So if we try to compute, say, this inner product using the path integral, and so since I'm using the path integral, I will put a bar over it. That has to do with the fact that a path integral probably needs to be interpreted as an average. But for now, just think of the bar as meaning gravitational path integral. So if I want to compute this using the path integral, then what do? I put, I here, J here, and then I sum over some geometry in between. I also have to deal with the fact that there could be a handle here or something, right? So I sum over topology again with I and J. Okay, that's how the path integral computes the inner product. Now to compute this thing, I actually need multiple copies. So let me just draw the picture for n equals 2. Okay. So then the idea is that trace of m squared, the bar over it, is equal to a sum over I and j of I, j, where I sum over just whatever fits in here, whereas trace of m quantity squared, bar, is equal to a somewhat similar looking sum, except now I put I, and j, because this is one of the copy of the trace, and this is the other copy of the trace. And again, I sum over whatever I can glue in here. But then the point is that whatever I can glue in there is going to be permutation invariant under permuting the top circles or the bottom circles. So for example, like just at leading order, right? There'll be something like there'll be a contribution like this, and then there'll be a contribution like this, and then there'll be some funny contribution like this. And so if you take this 3 terms and you sort of plug them into these 2 sums, you get the same thing. It's just these 2 diagrams get exchanged. These 2 geometries get exchanged. So in fact, these are equal to each other, and that's true for any n. And so you see that this equation here is true. And so indeed, the rank of the inner product matrix for closed universe is 1, just straight from the gravitational path integral. Okay. So any question about that? Maybe what I'll do is I'll scroll down. That seems better. The problem with scrolling down is that then I can't leave a bit of it still there, but it's faster. So I think I'll do that. Okay, so feel free to ask me to scroll back if you have a question. And then I'll give you one more argument. So this one is based on ADS-CFT. So this is a sort of more precise holographic argument.
How confident can one be with regard to summing over all manifolds that extrapolate between these 2 closed manifolds?
Yeah, so that's a great question, right? So of course that's kind of a postulate of the gravitational path integral, right? I can say that that rule is precisely the rule that leads to the page curve that goes up and down. So that has some appeal to it. If you start not including some geometries, then the ones you don't include will kind of be the same ones which would have led to the page curve going down in the black hole case. But yeah, I think in the end, the gravitational path integral is something that we don't really know how to derive from another starting point.
So what assumptions are you making about the 4-manifold geometry and topology classification-wise?
Yeah, I guess just that it's a valid cobordism, right? So that it's a valid manifold that has those boundary conditions. Yeah, and then the rule is you're supposed to sum over anything you can put there. Yeah,
but is the rank of n being 1, is it robust, taking into account our lack of knowledge of all 4 manifolds?
I think so. I think that I think that the sum being permutation variant is pretty robust. If the rule is that you sum over everything you can put there. If you start putting restrictions on what you can sum over, that's a different story.
Okay, thank you.
Yeah. Is someone else talking or I don't? Okay, no, okay.
Noise from the outside.
Okay. Okay, and so the last argument I'll use is based on ADS CFT. So this is restricted to a closed universe solution with negative cosmological constant. And this argument actually we could apply, for example, in 2B supergravity, using n equals 4 super Yang-Mills, so in some real example of holography. So the idea is I want to take, if you just think from the gravitational point of view, I want to prepare some state on some Cauchy slice of a closed universe. And I can do that by doing the bulk evolution back to some Euclidean ADS boundary. Okay, I have some closed Euclidean ADS boundary. And then at least from the bulk point of view, I can now evaluate the path integral, sewing things in, and that gives me some state here. And so let's take this Euclidean boundary to have circumference beta. And just to give us more options, let's imagine we put some operator OI in the CFT inserted on that Euclidean boundary. So this defines some state. We could call this state I, okay? And then if we want to compute the inner product between J and I, we just have two Euclidean boundaries. Here's OI, here's OJ. And then, well, from the bulk point of view, we would say we sew in some geometry here and sum over whatever we can sum over. But from the CFT point of view, this is very easy. It's just the partition function of the CFT on a disconnected space. So it's the product of e to the minus beta h OI times trace of e to the minus beta h OJ, okay? And this is a product, so it has rank 1. You see, right? It's just a function of I times a function of J, right? So this is the outer product of a vector with itself. And so straight from the CFT, almost immediately, we again see that the Hilbert space of the closed universe is one-dimensional. Okay, so that's as far as I was going to go with the review of why this should be true. So hopefully you're at least a little bit concerned, if you weren't before, that maybe there's something to this argument. But yeah, I'm happy to, again, have more questions about this. And then I'll go on to start trying to address the problem. Okay. So let me just, yeah, before I try to fix it, let me try to first illustrate a bit in a more concrete model the consequences of this. So let me do a simple gravitational model. So here I'm going to use the path integral. So this will be 1 + 1 dimensional gravity. And the action is very trivial. Actually, let me call it I, since S is entropy. So the Euclidean action is just minus some number S naught times the Euler character of the spacetime, chi of M, where M is the spacetime manifold. So this is a gravity theory because of the Gauss-Bonnet theorem, right? You can write the Euler character as an integral over the Ricci scalar, and it's kind of like, it's some topological theory of gravity. But then I'm going to add a matter world line with an index I. Okay, so I sum over topology weighted by the Euler character, but then there's a rule that there's also an index floating around. So for example, if I want to compute the inner product using the path integral, so since it's the path integral, I put a bar. It's kind of like what I had before. So we're doing 2D geometry, except now I have to put an I index and a J index that have to connect up. And then there'll be higher genus corrections to this, right? So here's some handle, here's I, here's J. The world line still connects through here. And if you add all that up, you just get delta ij over 1 minus e to the minus 2 S naught. Okay. So this denominator comes from summing some geometric series of the genus. So this is some So in this gravitational model, the inner product is preserved up to some issue with the normalization. We could multiply the states by the square root of this if we wanted to normalize it exactly to delta ij. Okay, now I really feel like I don't want to erase this yet, so let me scroll over here so you can still see it. Okay. On the other hand, we learned in the introduction that it's not enough to look at the inner product. You have to look at the inner product squared. You have to look at the fluctuation of this statement to decide whether things are really going well. And so indeed, we could consider Ji, Ij. Okay, we could try to compute that quantity. Okay, and what is that? Well, here's J, here's J. Okay, but then we can connect in these ways I was talking about before. So there's a geometry like that. There's a geometry like this. There's a geometry like this and also like this. And then there are higher genus terms that I won't draw. And so if we evaluate this, right, thinking about what the world lines do, there's 3 contributions. So from this term and this term, so remember there's I, J, J, I, we get twice delta ij. We get a delta ij from here, we get a delta ij from here. But then from this cross term, we just get 1. Because here it's I is automatically going with I, and J is automatically going with J. So there's no Kronecker delta, and then this is plus corrections that are suppressed by higher genus, okay, e to the minus 2s naught. And so in particular, this means now if we look at the fluctuation, which was the thing we were supposed to be looking at, Ji minus Ji bar, absolute value squared bar, okay, that's the fluctuation. We get 1 plus delta ij plus order e to the minus 2s naught, okay? And so this is order 1, right? We get order 1 fluctuations in the inner product in this model. And actually, this is the same order 1 fluctuations that we found back at the beginning with this model with the orthogonal matrix, okay? And so this is one way of motivating that model that I wrote down before. You have the, where you encode the bulk picture into a one-dimensional Hilbert space, and you get fluctuations which have exactly this form. There's another way you can phrase this result, starting from this equation, right? You can say that I define an observable, pi, which just asks, is the state I? Okay, that's an observable. And then I'm computing the expectation value of pi in the state j. Okay. And then what I got was 1 plus 2 delta ij. So in particular, if I is not equal to j, I still get 1. Which is a massive violation of effective field theory, right? Effective field theory would say, no, I has to be equal to j, or this projection should give 0. But somehow in the path integral, when we looked at these fluctuations, because of this cross-connecting diagram here, we see that even when I is not equal to j, the detector still clicks with probability 1, and so that's some big breakdown of effective field theory. And one that matches the code picture that we had before. Okay. All right. So yeah, go ahead.
So these matter world lines, so how should we think about these? These are like particles that sort of like are heavy and classical. They don't split into 2 particles, let's say, and that sort of thing.
Yeah, that's right. So you should think of them as being very heavy. This is some limit where the matter particles are very heavy and they carry a label. So it's a sort of cartoon matter of bulk matter, right? Model of bulk matter.
They still can undergo some kind of transition by.
Yeah, but we imagine that's suppressed by some parameter that I took to 0 in this model.
Okay.
Yeah, we could try to put in a more realistic matter and a more realistic gravity, and this conclusion would still be true. It would just, we'd have to work harder to get it. Okay. So that's it in terms of telling you the problem. Now I want to just say as much as I can about the solution in the time that we have left. So I'll aim to. We're actually not too far from the end. I mean, I think if I can have 15 minutes, that should be enough. That would be ending at 3:10 your time, I think.
Sounds good.
Okay. Okay, so now we want to try to fix this by including an observer. Okay, and so this is where things get kind of funny. I mean, well, you can say they're funny already, but now we're going to try to be funny with a good sign instead of a bad sign. So I want to include an observer, and so I have to assume. So of course, I don't want to get into a detailed philosophical discussion about what's an observer. You know, is my laptop an observer? Is ChatGPT an observer? Is an ant an observer? You know, okay. So I'll just tell you a few things I'll assume about observers without trying to be too detailed about it. So the first thing I'll assume is that the observer has some Hilbert space, which is exponential in something I'll call S observer. So this is the definition of S observer. It's the number of degrees of freedom in the observer. And what I'm going to assume is that how shall I say this? The uncertainty for that observer in whatever they measure is bigger than e to the minus S observer. Okay. So I just say, you know, if you are a human observer, your S observer is something like 10 to the 24, then you can't do experiments that are more precise than e to the minus 10 to the 24. Sorry. How would you even write down the result of the experiment if it was going to be more precise than that? So I think this is actually reasonable. I think, you know, usually in quantum mechanics, we sort of take S observer to infinity, and then we think that we can be as precise as we want. But if we're really going to have an observer of finite size, there's a limit to how much that they can learn. And that's going to be important for us. Okay. So that's assumption number one. Assumption number two is that the observer is approximately classical. Okay. And so here, as I was saying to Sezgin, there's a whole history of this where what that means in practice is that there exists a basis of states which are called a pointer basis. So a pointer basis is one which is stable under interaction with the environment. And so that's the work of Zurek and collaborators. So they say that what really makes a system classical is that it can be interacting with a big noisy environment, and yet the state of the system can be preserved for each element of the basis, at least approximately. So I don't want to give a whole review of that idea, but I'll just say it's not an idea I invented. It's an idea that's been around and I think is mostly accepted by people who've thought about these things. And then finally, I want to say that the observer is entangled with their environment E, and that the off diagonal components of rho observer in the A basis are small. Okay, and so all this is discussed in great detail in this review of Zurek. Okay. That's not Catherine Zurek, by the way. It's Wilczek Zurek or something. He's somebody at Los Alamos. Now, I do want to say that there's an important ingredient to this, which is that interacting with E is an example of what's called a quantum to classical channel, which means that it's a map on density matrices, which in the pointer basis takes a general state AB, or really just approximately gives you delta AB times AA. So a quantum to classical channel is just a map on density matrices that throws away all the off-diagonal components in some basis and keeps the diagonal components. And so you can convince yourself that that's a valid operation on density matrices, trace preserving, completely positive, etc. And so usually when you have a quantum system and it interacts with some big other system, then those interactions implement a quantum to classical channel, at least approximately. Okay, and so that's an idea that I'm going to need in a moment. Okay, and so in fact, that's it for my review of this stuff. I'm happy to discuss it more if people like, but let me now try to use it. Well, I should ask unless there are any questions about this. Yeah, okay. So let's now let me try to apply this stuff to the closed universe setting. Okay. So the idea is I've got my big orthogonal encoding map here that we talked about, and I'm feeding in this system M that I want to do experiments on, and maybe also this fixed state, which we don't have to worry about in this talk. And I'm projecting on to some fixed state because the inner product matrix is a rank 1 projection. But now I want to restrict to inputs where I have this matter system here that the observer wants to do experiments on. I have the observer, I have their environment, and they're entangled in some state omega. Okay, so I'm just going to restrict to these kinds of states. These aren't the only states that I could feed into O, right? I could also feed in states where there's no observer at all. But given how desperate I am and how severe, the problem is I'm not going to try to have a theory that makes sense when there's no observer at all. I will settle for a theory that only makes sense when there's an observer and that moreover only makes sense to an accuracy which is set by the size of that observer. That's the bargain which I'm trying to make here. Okay, so I just want to consider states like this, all right? And so we can, so in the language that I was using before, if I put a square root of d here, you can view this as a map which takes my old map v and feeds in this state omega on the observer and the environment, and then it allows an arbitrary input into the matter system. So v multiplied by omega on the right gives me a map from m to the real numbers. Okay. Now, this is not so good, right? And in particular, if I, so far I haven't solved the problem, right? So if I now, take a matter state phi, I hit it with, I put in v dagger v, I have omega for the observer and the environment, and then some state psi also for the matter. So these are matter, and then omega is omega here, right? Well, this just factorizes. So if you look at this picture, it's fairly clear, right? I get, let me write it like this. I get 0, O, and then I just get omega psi in this fixed state. And then just the same thing again, I get phi O transpose, and then 0. Okay, then I guess I multiply by d because there's 2 of them. Okay, but so this is just a product, right? This is a product of a function of psi and a function of phi, and that's this rank 1 inner product that was causing us trouble before. Okay, so far I haven't solved the problem. This line here is this omega. This line here is also omega. So the proposal. So let me keep this here. Okay, but is that in this inner product, I should make a replacement. I should take omega, which you see right here, sitting in between the inner product, and I should replace it by a quantum to classical channel acting on. Actually, sorry, it's the quantum to classical channel on the observer, tensor the identity channel on the environment. I don't want to do anything to the environment. Acting on omega. And so what that does is it replaces this inner product O by something where now there's a box here, O transpose 0, where this box is precisely the C observer tensor I acting on omega omega. But so the important thing is because of this box here from implementing this channel, it's no longer a product of the top and the bottom. The top and the bottom are now connected through this box, which was created by taking this state, omega omega, and just throwing away the off-diagonal components of the density matrix for the observer. And so this is the key step. I'm forcing the observer to be classical by taking what I would have gotten from a naive application of quantum mechanics and then just discarding the off-diagonal components of the density matrix, saying you're not an observer until I did that. I have to do that. And once I do that, you see I've now broken the one-dimensional nature of the Hilbert space by putting this box here that connects the bra and the ket. Now, to make it look more like what I had in the introduction, it's helpful to kind of bend the lines around a bit and put the, so like here's psi and here's phi. But to make it look like what I had before, it's better to put phi on top and psi on the bottom. And so if I bend the lines, then I get precisely this map V hat that I had before, where there's now this cloned observer. Here's omega. O, 0, psi naught, and M. Okay. Where this line is OB, this line is E. And then the final step to agree with what I had in the introduction is then I can just absorb E into OB here as a notational convenience. E is really there, but I can just absorb it since these two lines go in the same place. And then I get the picture that I had before where I just have one line going in here. Okay. And so that's the motivation for that diagram that I drew in the beginning of the talk, is that I'm splitting the observer off from the rest of the system, assuming they're entangled with their environment, and then forcing the observer to be classical by just brutally throwing away any type of quantum coherence between the observer and their environment. I'm keeping only the classical correlation and throwing away all the off-diagonal components in the density matrix. And it's just a proposal. I'm doing it because I think I should be able to get away with it since an observer should be classical, but that's the most I can say to justify it. Okay, so that's it for motivating the rule. I think it'll take me 5 minutes to say, maybe even less, to say what the results are. But let me ask if there are any questions about the rule.
Throwing away these octagonal terms, it's not a linear transformation, right?
Yeah, this is a linear map. Yeah, so this map that I drew, where did I write it? Here, this is a linear map. So I'm telling you how it's linear on the set of density matrices, right? So this C is a map on the set of operators. It's just in this basis, I just do this. So it's linear, right?
Not on the set of states, right? Not on the Hilbert space. I mean, it's not even an operator on the Hilbert space, but.
Well, no, it's an operator on the C is an operator on the set of operators. So it's a quantum channel. Right. It's a map from density matrices to density. Well, really from operators to operators, but in particular density matrices to density matrices. There is some nonlinear linearity hiding here, though. I'm not denying that, but it's not in this C. This C is a linear operation. Yeah, the nonlinearity is hiding in that what I've been using here, I've been using preserving the inner product here as a sort of indicator of preserving a reasonable semiclassical description. But in general, to preserve preserving the inner product only buys you some sort of nonlinear representation of the semiclassical quantum mechanics. Yeah, that has to do with how, but yeah, maybe let's not get into that now because then for now, I just want to have this be the story and I'll tell you what the result is. But I'll certainly acknowledge that in some sense I'm modifying quantum mechanics here, but out of desperation. Okay, so let me just quickly say to what extent this solves the problem, and then we'll be done. So let me go to results. Okay, so I define this V hat, right? So this V hat, remember this V hat goes from the matter system that we want to do experiments on to this Hilbert space of the cloned observer. This is OB prime up here. Okay. We can compute the same things we computed before. So we can compute the inner product in this code picture of V hat dagger V hat psi. Okay, and that's the same as phi and psi as before, but then we should really look at the fluctuation. Okay, and so now here's where the fun happens. So previously we had 1 plus the inner product of phi and psi, and we complained that this was order 1 and led to a large violation. But now I get e to the minus the second Renyi entropy of this state omega on the observer. Okay, so this is suppressed by the amount of entanglement between the observer and the environment. Because remember this omega state, it started at life as the state describing the entanglement between the observer and the environment. And so as long as the entanglement of the observer with the environment is of order the entropy of the observer, which I think it should be, certainly for observers like us, then this is an exponential suppression of the fluctuation in the inner product, which goes in the direction of restoring the validity of the semiclassical picture. Similarly, in the gravitational model, and this will be the last thing I say, and then I'll really be done. Sorry for going a little over. I can look at this kind of thing that I computed before, and it looks somewhat similar, right? We have these 3 contributions, right? Like this, and like this. But now they get decorated by this entanglement with the external system when you do the calculation. Okay, and then the result is that you get 1 plus delta ij, which is the sort of bad fluctuation that we found before. Oh, sorry, this is well, sorry, okay, this is for the square. Then to compute the fluctuation, I should do, I won't write it out. To compute the fluctuation, I get this. But again, now with the e to the minus s2 of omega observer, okay? And so in both cases, the sort of bad effects that were coming from the one-dimensional Hilbert space have been suppressed by the entropy of the observer who we treated as classical. And so to me, this is kind of, I wouldn't say compelling because this is kind of too crazy to be convinced immediately, but it's certainly very suggestive, right? It says that somehow if we make assumptions about the observer, which we kind of would make anyways, and which in fact exist in the literature already, and we're serious about them. We say really that until those assumptions are true, you're not an observer, then we can suppress the bad things that are coming from living in a one-dimensional Hilbert space. Yeah, I feel like that's interesting. I would like to think about it more and see if it really makes sense. But as far as I can tell, it's certainly the best thing on the market for making sense of this problem. The alternatives, like, for example, just not summing over these geometries at all, seem like they're going to get you in trouble in the black hole context. And so we need to think of something better. Okay, so I will stop there. Thank you. I'm happy to take questions.
Any questions?
I just have one question. For a 2D path integral, summing over topologies makes sense, but what kind of thing would you do for 4D?
Well, you still want to sum over topologies, I think. Yeah, it's true that our knowledge of 4 manifolds is a lot less than our knowledge of 2 manifolds. So doing the sum in practice seems totally impossible. But these leading order contributions don't seem impossible. They're just sort of simple cobordisms between the top and the bottom that make sense in any dimension. And then the harder, the more advanced geometries are suppressed by this topological expansion. So that's why I was able to just kind of only talk about these simple geometries and not all of them, is that the other ones are somehow suppressed exponentially in 1 over g Newton. And so I would guess that that's true in higher dimensions as well. 3 dimensions is currently the state of the art. People are working really hard on it. But already that summing over 3 manifolds is hard. There's various conjectures around for what should happen, but it's not a done deal by any means.
Okay, thank you.
More questions? Looks like we asked all our questions along the way. So thank you. Let's thank our speaker again.
Well, thank you. Thanks for attending.